Alright, hey everyone, so let's do solution number 3. Now, I kind of already drew it out for you guys, so let me just explain what's going on here. In this solution, again, just as in the previous examples, we're going to mix two different things. We're going to mix, in this case, a weak base and its salt. As a weak base, I chose ammonia, NH3. As its salt, I chose NH4Cl, ammonium chloride. Now, we're going to make the same assumptions we did in the previous two solutions. We have a bucket that just contains H2O liquid, and inside that bucket, we take some of the weak base and we toss it inside of this bucket. Well, what happens when a weak base comes in contact with water? Now, you guys have known this by now from chapters 15 and 16, that when a base comes in contact with water, the base is going to accept a hydrogen from the water, and you're going to form the conjugate acid and a hydroxide ion. We know this is a reaction that goes in the forward direction and in the backward direction, hence it's a reaction that's eventually going to reach an equilibrium state. Now, we know at equilibrium, as I've denoted it in previous problems before, it's essentially just, you can denote it just like this. Reactants, and the R stands for reactants, the P stands for products, and just as long as, this is a way of denoting that the reaction is at equilibrium. Now let's see the effect of adding a salt inside of the solution. Now if we look at the salt, ammonium chloride is a strong electrolyte, meaning that when you toss it inside of water, it's an electrolyte, it's a salt that's going to completely dissociate. So if I look at NH4Cl, NH4Cl will completely dissociate, and it's going to form an ammonium ion and a chloride ion as well. So if I ask you, well, what's the effect of this salt on this solution? We can say that this salt is increasing the concentration of Cl- inside of the solution, and it's increasing the concentration of NH4+ inside of this solution. So that means if I was actually to look at this particular solution, now I have more Cl- ions floating around. I have Cl- ions over here, over here, over here, and I also have a ton of NH4+ ions floating around as well. NH4+, 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 NH4+. So notice that's what this salt did to this solution. It increased the concentration of Cl- and it increased the concentration of ammonium, of the ammonium ion. Notice that, what is the common ion between these two reactions right here? You guys will notice I already circled it out for you, but the common ion is the ammonium ion in this case. So what happens, if we already said, right, we said before that this salt increases the concentration of NH4+ present inside of the solution. If I look at this top reaction over here, this one right here, the ionization of ammonia, we know that if we increase the concentration of the base, that this reaction is going to shift in the reverse direction. Because if I'm increasing the concentration of NH4+, I'm increasing the amount of products. So remember, I go to my scale and I increase the amount of products that I have, because NH4+ is a product of this reaction. If I increase the amount of products, if I look at that scale, the scale that I drew out here, you guys see how this scale is off balance? The question is, how do I bring this scale back to a balanced position? I take some of the products and I place them on the reactant side. So we already know that this reaction is going to shift from right to left. It's going to go in the reverse direction. What this reaction is going to do is that it's going to consume this excess ammonium ion present inside of the solution. And I want you guys, so that's really, this is all of section 17.1, but it's a very important section, like I told you guys before, because the reason it's so important is because you guys should know which way reactions shift when you have more than one component inside of a solution. So you guys notice in this particular example, all of the reactions are shifting in the reverse direction. But, there are going to be some scenarios where the reactions shift in the forward direction and stuff like that. So the most important part, what the technique that this section is trying to teach you is, which way do reactions shift when you have multiple components present inside of a solution. Now, I just want to go over two more solutions that I just want to talk to you guys about. Something that's going to really help you guys understand buffer solutions, which is the section right after this one. So let's look at two more solutions. We're going to look at the solution right here. So we can call this right here solution 4. We're going to look at another solution next to it. And we're going to call this right here We're going to call this solution 5. Let's look at solution 4 first, right? So I'm going to do the exact same thing that I've been doing in the previous problems. I'm going to combine two components together. In this case, I'm going to combine a weak acid, something like CH3COOH, and a strong base. Just what's a strong base? Give you guys a random one, something like sodium hydroxide, NaOH. That's a strong base. So again, we're just going to make the assumption that I have a beaker that just contains H2O liquid. I take some weak acid and I toss it inside of this beaker. What happens when a weak acid comes in contact with water? We've gone over this before. We know that these things are going to react with one another. CH3COOH reacts with water, H2O, and it produces the conjugate base, CH3COO minus, and a hydronium ion. And again, we know that this is a reaction that goes to equilibrium. So eventually, like I've done before, how do you denote equilibrium? Draw the little scale out. That, reactants, products. And just for the sake of showing equilibrium, we're going to show these little two dots there. And what they're showing is that you just have, this is a reaction that's reached equilibrium. So it makes sense so far, right? You have a beaker which contains water, and you took some of the weak acid, acetic acid in this case, and you toss it inside of the solution. Acetic acid reacts with water, producing the conjugate base, and a hydronium ion. And eventually we know that this is a reaction that reaches equilibrium. Now let's say that as soon as I have that solution prepared, I take some strong base, some sodium hydroxide, and I toss it inside of this solution. So strong base is NaOH. NaOH. Now what happens when I toss a strong base inside of a solution? Strong bases completely dissociate. So if we know that a strong base is going to completely dissociate, I'm going to form an Na plus and an OH minus. Notice what's happening in this solution. So right now we can say that these are the two reactions going on inside of this solution. We know that we have the ionization of CH3COOH, and we have the dissociation of the strong base sodium hydroxide. Notice, I want you guys to pay attention to something. Notice how the product of this reaction is H3O+. Notice how the product of this reaction is OH-. Do you guys remember in video 1 when I showed you that a hydroxide ion, whenever a hydroxide ion is in contact or present in the same solution with a hydronium ion, they're always going to react with one another. So we know that these two components are going to react with one another. So in fact, there are actually 3 reactions going on inside of this bucket. You have also OH-, a hydroxide ion, reacting with the hydronium ion, H3O+, and this is going over and it's forming H2O plus H2O. And these are all liquid. And this is probably the most important point to understand right here. For section 2, which is buffer solutions, you guys have to realize that whenever you have a base present with an acid, they're always going to react with one another. And remember why we said this, why do these two things react with one another? Because if we look at the K, the equilibrium constant for this reaction, the equilibrium constant is 1.0 times 10 to the 14. It is a humongous number. Look at that, 1.0 times 10 to the 14. 10 to the 14, that is a big number. And I told you guys before, we can look at equilibrium constants. This is what this is. An equilibrium constant. And we can view them as tendencies for reactions to happen. So if we can view an equilibrium constant as the tendency for a reaction to happen, what does it mean if K is a very large number? If K is a very large number, that means that reaction is very likely to happen. It has a high tendency of happening. So whenever a hydroxide ion is present with hydronium ion inside of a solution, they're always going to react with one another to make 2 H2O liquid molecules. So just to show you guys what's going on here then, we know that if these two things are reacting with one another and they're forming water, we can say that the concentration of OH minus inside of this solution is dropping, and that the concentration of H3O plus present inside of this solution is also dropping. Very, very important. Notice that when I added this strong base, that dropped this concentration. What does my scale look like now? If I was going to draw my scale, notice how it's going to look like this now. My scale, I have the reactants and I have the products. I have the same amount of reactants, but now my scale is off balance. You guys see how this scale is not balanced anymore? I decreased the amount of products inside of this solution. If I decrease the amount of products in this solution, which way does this reaction shift in order to go back to equilibrium? Again, chapter 15, you guys learned about Le Chatelier's principles. If we decrease amount of products, this is going to want to go in the forward direction. I want to produce more H3O plus because this reaction is consuming it. This reaction right here, if I look at this top reaction, this reaction is consuming OH minus and it's consuming H3O plus. If I'm consuming H3O plus, this top reaction, the ionization of acetic acid, wants to go in the forward direction to produce more H3O plus. Why does it want to produce more H3O plus? Because it's losing H3O plus in this solution. So it wants to compensate, it wants to create more of it because it's sensing that I don't have enough of it inside the solution. So that's the most important part. You know, like I said before, like I told you guys earlier in the video, whenever you look at these problems, especially in buffer solutions, you always have to know which way a reaction is going to shift. And notice that in all of these problems, we always started off with the weak acid, and we interpreted what does the strong base do, what does the salt do. And again, the main focus, the main purpose is to tell you guys which way does a reaction shift. It is incredibly, incredibly important to determine which way a reaction goes. Now let's do one more. So that was solution 4. We were mixing a weak acid with a strong base. And we noticed in this particular case that the reaction shifts in the forward direction.